belongs to a third group elements. These are belongs to third group. It is also called as inner transition elements. Known as inner transition elements. These inner transition elements consisting of two series. The first series is called as lanthanides. And second series is called as actinides. Lanthanides and actinides which are present in this. These lanthanides are called as 4F series. It is also called as 4F series. It is called as 5F series. Okay. So the lanthanides and actinides which are present in that, these 4F series consisting of the elements cerium to lutetium. Cerium to lutetium. These are the 14 elements which are present in that, and the actinides are actiniums to lawrencium. Easily to remember, these are the elements which are present in that. Okay. Cerium to lutetium and actinium to lawrencium. These are the elements which are present in that. Okay. Each series is consisting of 14 elements. Lanthanides are 14. Actinides are the 14 elements. So total 28 elements are present. Why they are called as inner transition means when you take the elements of the third B group, or you can say third, we are having of scandium, yttrium, lanthanum, and actinium. These are the elements belongs to scandium, yttrium, lanthanum, and actinium. Here in the lanthanum, whatever the element, the 14 element, cerium to lutetium is present here only. And also on the actinium, from this actinium, we are having of the elements, okay, up to lawrencium. Up to lawrencium, we are keeping here only in the one box. So the modern periodic table or Moseley's periodic table, what they think is, whatever the scientists are thinking that, you can't fix all the elements, including of lanthanum is 15 elements, including of this one means 15 elements are there. How can you arrangement in this one box? It is very difficult. That's why they keep on the bottom of the periodic table. So on the bottom of the periodic table, they arrange the 14 elements like this. Okay. These are the 14 elements which are present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is called as a 4F series. It is called as a 4F series. Now, this from the third B group elements too, we are having of the second B element, that is a zinc, cadmium, mercury. These are all are D black elements. These are all nothing but D black elements. D black elements are called as transition elements. Why it is called as a transition? Because there is a S group and there is a P group. In between it is there, these are the transition. Here, why it is in the transition? In the transition, there is again 28 elements are present, so that they are called as inner transition elements. That's it. Inner transition meaning of nothing is the elements which are present in the transition only. in the transition group only. So that those are present in inner. That is inner means after the lanthanum, you are having of the cerium to lutetium. Those 14 elements we are keeping on the bottom of the periodic table. It is called as a 4F series. It is nothing but it is a name of the 4F series is called as lanthanides. Right? Because it is starting from the lanthanum. Again, remaining other same under the same group actinium. After the actinium, we are having of the up to lawrencium, the 14 elements are there. Those are called as actinides. That is called as the 5F series. 5F, 4F, why you are calling? The electrons are entered into the 4F orbital. All the 14 elements electrons are entered into this one 4F series. And the remaining one 5F series, they are entered into the 5F series. This is about the story of the particular inner transition elements are 4F or 5S series. Okay, fine. You are getting of the little bit of having of the this particular idea. And coming to the general electronic configuration of F block elements is actually previously this which is having of the section C, a multiple choice question, and these are the important questions. So, general electronic configuration. General electronic configuration of a block element is nothing but inner transition means N minus 2. This is the penultimate shell. F 1 to 14. Why? Because F orbital can accommodate 14 electrons. So, F orbital is up from 1 to 14. Next, N minus 1, D, 0 or 1. Sometimes there is no electrons in the d orbital. Sometimes only one electron is there. That is a penultimate shell. This is anti-penultimate shell. Penultimate, anti-penultimate. Last outermost shell is nothing but NS2. S orbital. So this is a general electronic configuration of a block elements is N minus 2, F 1 to 14, N minus 1, D 0 or 1. 0 or 1 NS2. This is a general electronic configuration of inner transition elements. Either maybe a 4F series or maybe a 5F series. Okay. So this is called as inner transition. Now coming to the 4F. 4F block means first series of the F block element that is comes under the cerium to lutetium. That means 38 to 71. The atomic number cerium is 38 and lutetium is the 71 atomic number is there. Okay. So, sorry, lanthanum is the 57th element, cerium is the 58th element, 58 to 71. Yes. And actinium, after the actinium, you are having of the remaining other elements which are present in the 5F series, that is from 90 to lawrencium 103. 90 to 103, 14 elements which are present. Those are called as a 5F series. So 98 is thorium. So actinium, these are after the actinium, we are having of the thorium to lawrencium. This is 90. It is 103. Before that, we are having of the lanthanum 57. Actually, lanthanum belongs to D black. Actinium belongs to D black. From this one only, we are having of this is the 4F series. Cerium to lutetium, thorium to lawrencium. Thorium to lawrencium is nothing but we are having of the 5F series. That is the actinides. Okay, this is a general electronic configuration. Please remember what are the classification of F block elements means. F block elements are classified into two series, lanthanides and actinides. Lanthanides are called as a 4F series. That means the last electron entered into the 4F block, and the actinides means the last electron is entered into the 5F series. And what are the elements? 14 elements. This particular series is consisting of 14, cerium to lutetium, actinium also 14 elements from the thorium to lawrencium. General electronic configuration. Okay. So what are the general property means? Already I told in the D block elements, the general property means we have to write the electronic configuration of the lanthanides from the cerium to lutetium. It is not, means sometimes only we are asking question. Why? Because you can't remember the cerium to lutetium 14 elements easy, not easily. Only the D block elements, 3D block. That's why I'm using of 3D block. At least you have to remember from scandium to zinc to getting of the writing of the electronic configuration. Here, no need to write electronic configuration. Just to remember the names of that one. And here, in this particular F block element, the common oxidation state is +3 for the both lanthanides and actinides. From the lanthanides and actinide, the most stable common oxidation state is +3 only. But remaining other maximum is also present. You know that variable oxidation state is present from the D block element, but not the F block element variable. Only few are there, few elements which is showing of the different electronic configuration. That means the different oxidation states will be showing up that one. This is about the lanthanides. And in this main important the question is what is lanthanide contraction? Everything it is a repeated question. Means in A, B, C set of the papers, compulsory any set of the paper, this question will be obvious. What is lanthanide contraction? Lanthanide contraction is nothing but if you see the elements from, let's say I'm writing of the 3D black elements and the third B group elements, and it is also called as 3B or third group. These are the group. It is a group. Okay. That means F block elements are belongs to third group elements only are Roman letters. This third group. That is it comes under from scandium, yttrium, lanthanum, actinium. Okay. This is the third B group element. These are belongs to the 14 elements lanthanides. Cerium to lutetium is present here only in this box only. That's why you are keeping at the bottom of the box. Actinium, 14 elements present here only. There is no place to keep all the 14 elements in the one box. Means due to that reason, we are keeping at the bottom of the periodic table so that these are the inner transition elements. Here, this particular lanthanum is called as a 4F series. Why lanthanide contraction? Means if you see the whatever the size, atomic size, in any group, what happened? From top to bottom, atomic size is increases. Why it is increases? Because of the number of shells are increasing. Orbits are increasing. So that electrons are entering into the new orbits only. Due to that reason, the atomic size is from top to bottom, it is increases. But here in the lanthanides, the electrons are entering into the 4F series. That means here this particularly nucleus, first orbit, second orbit, third orbit, fourth orbit. In this S is there, SP is there. Here SPD is there. But here SPDF also present. In the fourth orbit. In the fourth orbit, F orbitals are entering. If the F orbitals are entered, the electrons are entering into F orbit. This particular F4F orbital act as a shield. It acts as a one shield before the electrons, after the electrons. So that what happened actually, that generally the atomic size is increases from top to bottom. Automatically lanthanide from cerium to lutetium also, you must increase the atomic size little bit. Why? Because it is in the same box. But here what happened? Due to of the 4F block elements, it act as a 4F series act as a shield is acting. That means it is act as a shield. This electron does not attract it towards the nucleus. Only these 3 orbits, electrons only attraction towards the nucleus. Due to of the shielding effects, the increasing of the size, what happened here? Decreases. Due to decreasing of size is called as lanthanide contraction. What do you mean by the lanthanide contraction? Means nothing is there. Actually, in any group, the size is increases from top to bottom. That is the rule. That is a property of the periodic table. But here what happened? When the 4f orbitals entered or the electrons are entered in that one, that 4f black is act as a shield of the remaining other electrons. It can act as a shield or screen. The screen of the electron means whatever the electrons are entered into the 4s2 or 4p6 or 4d10 or 4f. These electrons are does not attracted towards the nucleus. Only these electrons are attraction. That's why the size will be actually increasing size. It will be decreases. The decrease in size is called as lanthanide contraction. That is nothing but. Okay. You may understand the easily this particular lanthanide contraction means. This is a compulsory question in your textbook. Page number is 20. It is clearly given cause for the lanthanide contraction. That is important question of this one. And remaining whatever the properties. Already told that D black elements are metals, A black elements also metal. They show also magnetic property. It is also magnetic property. They are also D black elements showing the color property. These are the color property. But some elements showing here color properties. That we'll discuss about the similarities and difference between the 4F and 5F series. Okay. First, we have to remember what is lanthanide contraction and the magnetic properties here, and also complex compounds also formed by these particular elements.
Sir, how many of them we should write if they ask for 10 marks?
My year in the F black elements, don't ask the 10 marks question of this particular. These are all of bits only. Only lanthanide contraction means that is only the 5 marks bit. That is 10 marks is what is the similarities, what is difference between the 4F and 5F series. Number of points are there. Okay. For this one, we are having of only small concept. Why it is happening? What is this series? You have to know. Then only you can write the what are the similarities, what are the differences are present between the 4F and 5F series. That's
sir,
it.
Any chances that we will get 20 marks from this chapter?
No question. If they are asking the 20 marks question means they club the 4, that means D black and F black. That means one question belongs to the D black, one question belongs to the F black. Maybe chance.
Yes, sir.
Like that. A and B. That is question. Okay.
Okay.
Now, coming to the what are the reactivity of lanthanides? Particularly, they are having of textbook that is a page number 22. We are having of in that so many number of points are given. What are the reactivity of the lanthanides? In that few points are mainly important points. This particular lanthanides are white in color. But when you are exposed to air, the color will be tawnish. That means comes under the some yellowish gray color will be formation. And also these are the formation of when you are burning the air, these particular 4F series, cerium to lutetium, they are formed the superoxides. That means superoxides will be nothing but the form, peroxides will be formed. The peroxy nature will be, that means between the oxygen and oxygen, a bond is formed. That is called as a peroxy bond. So here only the 4F series is the reactivity is more due to that they are having of that one. And also they dissolve so slowly in the cold water, but in the warm water, easily dissolve will be takes place. That means in ordinary temperature, at room temperature, that particular 4F bulk, whatever the elements, does not dissolve properly. But lukewarm water, it will be dissolved very easily. And hydrates form, nitrogen with the, it is reacted with the nitrates are formed. These are the strong reducing agents. And also, it will be act as a, that means attracted to the acids. These are important reactivities of the particular lanthanides only. And the lanthanides, particularly, what are the, this question will be asking in your example, what are the uses of the lanthanides? Mainly, for the 5 marks bit. What are the uses of the lanthanides? Means, particularly these lanthanides is, they are used as a alloys. That means, cerium magnesium alloy. This which is used as this particular alloy is used in the cigarette lighters. That a flashlight will be obtained. This alloy is used. Why? Because the light will be glows easily by the triggering of that particular lighter. Okay. This is the particular uses of the lanthanide. And also cerium is used for preparing of particularly sunglasses. The film is coated, cerium film. that will be UV protection will be taken by this particular cerium. That's why in the sunglasses, cerium element is used in the protection purpose. Okay. And also these particular four lanthanides are used in the lasers. Laser technology, that means flashlights. The flashlight is nothing but you are using the laser technology. And also these particularly lanthanides act as a catalyst also. But the black elements are good catalysts compared to the any other elements. These are the act as a catalyst also. Okay, this is about the what are the uses. Only few 3-4 points are there for the particularly uses of the lanthanides. Okay, now coming to the actinides. See in this lanthanides, what is the question up to now is what is lanthanide contraction? Next is what is the uses of the lanthanides. In that particularly lanthanides, we are study about the that means we are know about the cerium only. Why? Because cerium alloy is used as a cigarette flashlight or you can say flashlights also. And also these particular cerium metals used in the laser technology and some of the lanthanide element act as a catalyst also. That is the uses of that. These two questions only important for your examination. Coming to the 5F series. 5F series is nothing but the actinides. These also 14 elements are present. That is from the thorium to lawrencium. See here, cerium to lutetium is, these are all are non-radioactive elements. But the 5F series from 92, that means we are having a from after the 90 element, these are all are radioactive nature. Can you say the radioactive elements you can study the properties? You can't. Why? Because radioactive nature means spontaneously emission of certain rays. When you go through the study of the any properties, it will be turned to the other elements. So that is not that much of easy to study the properties. That's why the 4 and 5 series is a peculiar properties are there. There is a differentiation between the what are the similarities, what are the differences. They are asked for the 10 marks question, sometimes maybe 20 marks question. One of the student will ask, sir, 20 marks means this is the similarities and differences. Maybe chance. We have to write the both the similarities. What are the similarities are there? What are the differences between the 4F and 5F series? That will be there in your textbook. That is page 23 and 24. Few points are given. What are the comparison of the lanthanide actinides? What are the similarities? Similarities are already told the common oxidation state is +3. And also I told that those are all, both are the paramagnetic in nature. Both 4F series and 5F series are act as a paramagnetic in nature. In our book, that this point is not given. You can add this point. Both similarities means these are act as a paramagnetic nature. 5F series also act as a paramagnetic nature. And also these are particularly both the elements having of this particular 14 elements, lanthanides and the actinide 14 elements having of low electronegativity atoms. That means less reactivity will have. Due to of the low electronegativity, their reactivity is less. When you are comparing that the 4F and 5F is almost all these are the radioactive elements. These are the non-radioactive elements. When you are writing in the difference, but here similarity you are writing means these similarities are there plus common oxidation state is +3. Both are the paramagnetic nature and both are having of low electronegativity. Due to that reason, they are less reactive. That's it. And also both showing of ion exchange character. That means the character will be that you use as a ion exchange. That means one atom will be losing of the electron and is a gaining. Here only the gaining will take place. Ion exchange character will be takes place in the 4F and 5F series. And in this particularly, already I told that when you are dissolving that, the superoxides are perchlorates, sulfates. These are all are soluble, but lower oxides that carbonates are insoluble. Only perchlorates and sulfates are soluble in water, but the carbonates and also fluorides, which are not soluble in water, these are the important similarities of lanthanides and actinides. Coming to the similarities, differences, when you are taking up the differences, it is a beautifully is given in your textbook. Those points is enough for your examination point of view, even though it is a 10 marks question. Suppose the 20 marks question means you have to write both the similarities as well as the differences. Now coming to the differences. You can write easily to remember for your examination part. What are the differences? Lanthanides. These are elements are the electrons are enter into the 4f series set. Lactinates. The electrons are entered into the 5f series set. This is the one difference. The electrons are entered into 4f series is called as lanthanides. The electrons are entered into 5 series is called as actinides. That's it. Okay. And also the bonding energy of the 4f orbitals are very high. Bonding energy. So bonding energy, if it is a 4f orbital is high, means automatically 5f orbital is less. And also, just now I told that lanthanide contraction is there, but not actinide contraction. Why? Because it is again the one more series is there, one more orbit. If it is already a shield, a screen is established here, what is the need of the screen again? That's why 4F series is actually having of the a great shielding effect or screening effect. It is called as due to of the shielding effect or screening effect, the size is decreases instead of increasing of size. Only inner orbital electrons only attracted towards the nucleus. These electrons are not attracted because of the screen is established or formed between the 3D and 4D. In between, a screen is formed due to of the 4F series is entered. Okay, that you have to remember. And in this, the lanthanides, before you know that, but the acid is variable oxidation state of d orbital. I told that the maximum oxidation state of 3D is +7, 4D is +8, 5D also +8. Ruthenium tetroxide, osmium tetroxide, there is a +8 oxidation state is there. In the third 3D series, only +7 potassium permanganate is there. But here, actinate, the maximum oxidation state is +4 only. Common oxidation state is +3. Maximum oxidation state of 4F series is +4 only. That is called as ion exchange character. That means most of the electron does not loses formation of the bonding formation. Only few electrons are 3 or 2, 4 electrons will be. So +4 won't be the maximum oxidation state, but 5F series is they are having a +3, +4, +5, +6, +7 also. This is a difference. Easy to remember. One point is that belongs to 4F, that belongs to the 5F. High bonding energy, low bonding energy. Maximum oxidation state +4, maximum oxidation state +3, +4, +5, +6, +7 also. They form easily complex compounds. Already told the D plug elements are formed the complex compounds. That is given as so many number of examples. Hexacyanochromium chloride, hexacyanoferrous ferrate or 3-chloride ion. These are all are tetracarbonyl nickelate. Yesterday the complex compounds we have discussed. The same here 4F series can easily form the complex compounds, but there is a less tendency, show the greater tendency of this particularly 5F series. And here mainly one more important point is these are non-radioactive nature, these are radioactive nature. This point must be right. Remaining are the common. So 4F, 5F anybody can write. And also bonding energy will be there. They are the less formation of the complex compound. They are more formation of the high lead formation of that one. But these are the non-radioactive elements. These are radioactive elements. If you observe the radioactive elements, Right. And the next is one more also you can easily remember. 4F series, most of the ions. Why ions I'm saying? Because of vacant f orbital only, showing of the properties due to of the availability of the electrons, not fulfilled electrons, incompletely filled electrons only. Here, the 4F ions are, most of the ions are colorless compounds. Actually, the properties of the D black, all the D black elements except secondary group, zinc, cadmium, mercury is colorless. Or you can say D0 or D10 electronic configuration is colorless compound. Remaining all are colors, but here 4F dark elements are colorless compounds. But 5F series are colored compounds. You can easily remember differences. These are colorless, these are the color compounds. And both are again the similarities. 4F series are paramagnetic nation. These also act as a paramagnet, even though those are the radioactive elements. Radioactive elements actually you can't explain the properties easily, but they can act as a paramagnet. Paramagnet means they attract the magnetic field. Okay, that's why they are adding up. Due to that one paramagnet nature, these are 4F series are less ionic in nature. Why less ionic in nature? Already I told that the maximum oxidation state is +4 only. If the number of electrons will be loose, means getting of the more oxidation state. But the 5F series, we are getting of the +3, +4, +5, +6, +7. That's why the more ionic nature will be there of the actinides. Less ionic is there the lanthanides. These are the enough points for your examination point of view. In this essay type question is only one, that is what are the similarities, what are the differences between the lanthanide and actinides. And the 5 marks question is what is the lanthanide contraction? One question, what is the uses of the lanthanides? That's it. This is about the second unit of your black universe. Now we will go to the third unit, that is coordination compounds, coordination chemistry, and you have one. That is a very important your examination point of view. One is some of the theories are present. That is Werner's theory, crystal theory, valence bond theory. These are the theories are which are present in that chapter. So the next is coordination compounds. In that coordination compounds, first already I told in the D block what is double salt. First question, what is coordination number? These are 5 marks questions. What is double salt? See, this question also compulsory in any one of the set paper. And what is the coordination number? What is the ligands? Classification of the ligands. Ligands are classified into monodentate, polydentate, didentate. There is a mono, di, polydentate. Like this, what you are having of the different compositions will be there. So in the your textbook, that is the page 26 is there. Yesterday, I already told that what is the double salt means. Double salt is nothing but double salt is a one in which individual components does not lose their identity. Double salt is nothing but it is a mixture of two salts. In this, what happened? Individual component does not lose their identity. Their own identity, whatever the identity is present, that will be present in that double salt. But they exist as a single unit only, in which is in crystalline state. You can't identify only by means of the semi-micro analysis. We can identify in this we are having of the double. That means one may be a potassium, one may be a chloride, and that means cation, anion. Two cations are there, two anions are there. Due to that reason, this is called as a double salt. So in the examination, just define it and give the example. Yesterday I given the three examples: carnallite, potash alum, more salts. These are the important double salts. So double salt is the one in which individual component does not lose their identity, but they can exist as a single unit in the crystalline state is called as double salt. Example is a carnallite, KCl, MgCl2, 6H2O. Carnallite formula you have to remember. KCl, one salt. MgCl2, one salt. There are double salt, in which one six hydrated molecules are there. So you are combine a single unit, one crystal salt will be there. That will be called as a double salt. Okay. Next, we are having of the coordination number. Coordination number is what? Nothing but the coordination number is when central atom is present, how many number of ligands are surrounded by the central atom. Number of ligands are surrounded by the central atom is called as coordination number. If the coordination number is 6, it is the structure of that particular complex compound is octahedral. If the coordination number is 4, that means what? 4 means only 4 ligands are surrounded by the central atom. 6 ligands are that means surrounded by the central atom is called as octahedral. 4 ligands are that means surrounded by the central atom is called as tetrahedral or square planar. That will be using of that particular compounds. Okay. So that is about the your coordination number. And ligand means ligands are an ion or neutral atoms. The ligands may be a neutral molecules. Neutral molecule means ammonia is a neutral molecule. Ethylene diamine is a neutral molecule. Pyridine is a neutral molecule. Okay. So in the ligands, we are represented as ammonia. Ethylene diamine, EN, we are representing pyridine, PY. These are all are the valency. That means we are using oxidation state is 0. Means it is a neutral ligands. I hope you can understand the ligands means what? A central atom is there. M is a central atom. It can be surrounded by, I'm using this other surrounded by the ligand, whatever that one. I'm using the X. These are called as a X is called as a, this means X is a ion, not neutral atom. It is surrounded. How many number of ions are surrounded? 6. The coordination number of the central atom metal is called as a 6 coordination number. It is octahedral structure. That's it. So neutral ligands are ammonia, ethylene diamine, pyridine. So I'm writing the symbol of ethylene diamine is En. Pyridine is Py. And ions, neutral, that means negative ligands are cyanides, which hydroxide ion and also cyanide, OH, and also remaining other already you are having of the halogens. That means your X you can use as something fluoride. X. These are the negative ligands. Okay. So on the basis of the neutral ligands or negative ligands, it is surrounded by the central atom. We are getting of the a complex compound is formed. Okay. Now in this nomenclature of the coordination compound, they are asking in the examination compulsory a 5 marks bit. Nomenclature. They give in the some complex compounds. On the basis of the complex compound, you can identify the write the IUPAC name. So writing of IUPAC name, I will write sometimes they will give the name of the compound. You can write the complex compound. Either that or this one they are asking in the examination. So in your book, it is given as page number 28. Tetracarbonyl nickel. Structure is not given. Suppose in the examination, tetracarbonyl nickel oxidation state is 0. There is it is a 0 means carbonyl compound is there. Carbonyl compound is a neutral atom, neutral ligand. Tetracarbonyl. Carbonyl means carbonyl. How many? Tetra. Nickel. Nickel is the central atom. So it is a complex compound. That's it. See, writing of IUPAC nomenclature is very easy. Sometimes they give the structure, you write the name. Tetracarbon and nickel. That is given. In your book is given the word form. You can write the structural form. Next, dichlorodiamine platinum 2. Dichlorodiamine platinum 2. Means the central atom is having the oxidation state is +2. That indicates. So amine also neutral atom. Chlorine is there. So that first central atom is you are identify the central atom. This is the ligand. This is the ion. Here this is the central atom. This is the ligand. Now write the platinum first central atom. Platinum. How many amines are there? 2 amines. Diamine. NH3 2. It is complex compound. We are putting to the square brackets. How many chlorines are there? 2 chlorines. Cl2. So ammonia, it is a neutral, 0 oxidation state. Here each chlorine is a -2 means it is -2 comes under here +2 means it is a +2. Okay, this is a writing. Don't write these oxidations actually. +2 means it is indication. Okay, so it is a +2. That indication of +2. So dichlorodimine platinum means this is a structural formula. Next, third is given what? Hexaamine cobalt chloride. Hexaamine cobalt 3 chlorides. I hope already yesterday I write the structural formula. Cobalt is the central atom. Amine is a ligand. Chloride is ion. So hexaamine. Amine means ammonia. NH3 6 hexa. Cobalt is a central atom. It is a 3 means it is already 0. Chloride means 3 U1 means Cl3. Then it comes under here +3 oxidation state, cobalt +3. That's it. Are you following me? Idea to write the formula or IUPAC nomenclature. This is the formula structure. It is IUPAC nomenclature. Next, one more is given. Better why? Because the structural formula is not given in your book. You can take the structural formulas also. Fourth one, it is given as potassium hexacyanoferrate. Ferrate 2. Oxidation state of the ferrous is a 2. That means ferrate is the central atom. Cyano is the ligand. Potassium is the prefix of that particular complex compound. Potassium. K. Write the square brackets. Ferrate. Iron. How many cyano group? Cn. Hexacyano. What is the ferrate? It is 2. Actually, if you are not putting any number here, potassium, the cyanide, each cyanide is -1, means -6. -6 means +6. Ferrous is +6, but is given as a 2. That means potassium ions are present. How many are there? 4 are there. K4, Fe, Cn6. Then it is a -6 +6. We are getting -4 +2. 6 minus 4. 2 will get them. Okay, +2. This will be. The formula is K4, Fe, Cn6. That is given in your book textbook. It is also asking 5 marks bit. This is 5 marks bit. They ask so many times. It is a repeated question. And also in the last, that is the 6th one, is also given as hexaamine cobalt. Already you are having ethylene diamine chloride is also given. Okay, such compounds are present. So better to practice of this particular complex compounds. Now coming to the theories of the coordination chemistry. The theories, main important theories which are present here. Werner's theory. So what is the Werner's theory? What is given as a complex compound? In that Werner's theory, already I told that we are having of the primary valence is there, secondary valence is there. In that primary, secondary valence, how their arrangement will be takes place, we show the Werner's theory. This is 10 marks question. Werner's theory, crystal field theory, and also valence bond theory. The three theories are there in your textbook, page number 30, page 30 and 31 is there. Okay. Now, Werner's theory. Werner is explained this theory in the complex compound. Particularly, they use it as hexaamino cobalt 3 chloride ion. He explained with the complex compound, that is, the example is taken as the Werner's theory. Hexaamine. Okay. So, hexaamine cobalt 3 chlorides. This is the complex compound is taken. First, write the structure. Cobalt is the central atom. Cobalt. Amine is a ligand. How many amines are there? 6 amines are there. It is a neutral atom, neutral ligand, 0. But here, cobalt is consisting of the 3 oxidation state is there. Due to that reason, 3 chloride ions are there. Okay. It is taken as a one example of the Werner's theory. He explained with the how many number of primary valencies, how many number of secondary valencies are present. It is explained that one. In this case, particularly, here 6 ligands are attacked by the central atom. That means the coordination number is 6. It is a octahedral structure. That's it. Okay. How can you represent the primary valency? How can you represent the secondary valency? Means they give a number of structures. In that, how the complex compound will be formed. Say they given as, first of all, I give the first structure of the Werner's theory. Cobalt is the central atom. And here, see the structures. 4 are there. And also ligands. Okay. This is ammonia. It is ammonia. It is ammonia. Ammonia. Okay. These are all solid line. Solid line is secondary valency. Now they are having of. See, I am writing off. Okay. So better first category represent 1. This is chloride. Means it is a dashed line, means it is a primary valency. And the remaining, not here, why? Because the structure will be like this. 1 chloride. This is the first structure given by the Werner's theory. In this case, what happened? This is the cobalt chloride. 6 ammonia ligands are attracted. 3 chloride ions and 6 ammonia molecules. See, the next structure, how can you modify this one? It is modified as, this very simple here. How they are arranged is just very easy. Write it as 4. Okay. 1, 2. Next primary valency here only. See here. See here. See here. Here a solid line means secondary valency. Secondary valency. Secondary valency. Secondary valency. Second. That means it is CO cobalt chloride 3, but ligands are 5 ligands are there. 5 ammonia. The Werner is explained with the, you are decreasing the number of ligands. How the complex compound is possible? Whether it is the stable or not, this is the stable complex. Example is given as, here the primary valence is 3, secondary valence are 6 are there. Due to that reason, secondary valence is 6 means this is a neutral ligand. Those we are getting off the 0, but when the primary values are 3 are there attracted, this is why the cobalt chloride cobalt is getting of the 3 oxidation state. We are getting off only two oxidation states. It is less stable than this one. Like that, four amino, three amino. If you are observe here, I can write the this is second structure, third structure, cobalt, okay, four, and in this we are having of this is the one, and here you want the solid lines as well as the dash lines. You can also write like that only. Both primary and secondary valence are clubbing. Okay, this is a chlorine. It is a chlorine. It is a chlorine. Three ions are over. Remaining solid line, the secondary valence will be four. It can also possible. It is a square planar. Four ligands are attracted to the central atom. Tetrahedral structure. That means here the cobalt, chloride, three, four ammonia molecules are present. Only four are present. Okay. So one more structure also possible. This is the third structure. One more structure like is given as a Werner. The Werner is given as these are the three are trigonal planar. That means secondary valency is the trigonal planar structure. And three are solid lines and three are dotted lines. The three are arranged as like this. ClCl. That means the structure is COCl3, but the ligands are only three are there. Three amino. This is the fourth structure is given as Werner. Which one is the most stable is explained. Among this one, they are having of the single secondary valency and single primary valency. This is the more stable than this one. This is a stable than this one. This is stable than this one. The primary valency, secondary valency are combining so that you are getting of the trigonal planar structure. It is a square pyramidal. That means in the square natures. Square planar, sometimes a tetrahedral. But this is a complex compound. You can't say that. Then the only 4-5 ligands are distorted octahedral. That is, it is a complete octahedral structure that can be explained by the Werner's theory. In the examination, sir, what can write this one? Nothing is there. Only you have to draw these four structural formulas. Every time one ligand is reducing. Here 6 ammonia is there. Here 5 ammonia. Here the 4 ammonia. Here the 3 ammonia structures are there. These are all explained by the Werner's theory. How the complex compounds are stability will be depending on the stability will be on the basis of the ligands only. On the basis of the ligand, that means secondary valency only. When the secondary valency will be linked with the primary valency, then only the stability will be attracted. Here the secondary valency is the nothing but the ligands is means solid line is represented as the secondary valency and the dotted lines is represented as the primary valency. This primary valency is showing of the oxidation state of the central atom. So this is the indication of the oxidation state. That's why we are not disturbing the chloride ions. Oxidation state is already fixed one +3. But here, this is a neutral ligand. You can change the neutral ligand because oxidation state is 0. This is a neutral. Due to this, so many number of variables, that means possibility of the structures will be, these are the 4 possibility structures is given by the Werner's theory. So I hope that this is a very important in your book. That is a page number. It is given as 31, but not that much of good. Easy to remember. I hope you can easily remember these 4 structures in the examination point of view. Okay. Next, we are having of the Sirjevic electronic interpretation theory is also there. Sirjevic is given as the interpretation theory. In that, main important is effective atomic number is explained by the Sirjevic. That is very important by the in this particularly electron effective atomic number. Compulsory question in the examination point of view. By it is explained by the Sirjevic interpretation. Where this is a particularly Sidgwick is explained. Sidgwick theory is explained the effective atomic number EAN. Effective atomic number. What is effective atomic number is nothing but when the complex compound you are getting of the effective atomic number, it is compulsory a noble gas element atomic number is explained. Noble gas atomic number is attained by that particular complex compound that is more stable, it is explained. Werner's theory explained on the basis of secondary and primary valency only. When the secondary primary valencies are more, that means easily present means that is a more stable. But Sidgwick is explained on the basis of effective atomic number. What is effective atomic number is nothing but it is given as oxidation. That means central atom atomic number of central atom atomic number of central atom minus oxidation state of central atom. Okay, then you can add as 2 into number of ligands. By this formula, you can calculate the effective atomic number. Effective atomic number is calculated. Which formula means it is also not given clearly in your textbook. Effective atomic number means atomic number of central atom minus oxidation state of central atom 2 into ligand. Let us see the conclusion of just now you have discussed with Werner's theory. Now this is the oxidation state is +3. Okay. Central atom cobalt. Cobalt is what is the atomic number of the cobalt? Manganese 25. Ferrous 26. Cobalt is the 27. Okay. Cobalt is that means effective atomic number. Cobalt atomic number is 27. So 27 minus oxidation state is +3. That means it is a -3. Okay. Plus 2 into ligands means 2 into 6 ligands are present. So 27 minus 3 means 24. 24 plus 2 plus 12. It is nothing but 36. 36 atomic number what? Neon, argon, krypton atomic number. This is a krypton atomic number. If the atomic number is attained by the noble gas element, it is a very stable. That is explained. So in this theory, that will be happened. This will be, it is a great theory which is explained by the Sidgwick theory on the basis of effective atomic number. So in the examination, they ask what is effective number, effective atomic number. Calculate the effective atomic number of the sum of the complex compounds. So you can remember this formula. Atomic number of central atom minus its oxidation state plus number of ligands are multiplied with 2. That we will getting of effective. If the effective atomic number is next, that whatever the noble gas element atomic number, that particular complex compound is more stable. That will be explained by in Sidgwick theory. Okay, ma. So this is about the Sidgwick theory's effective atomic number. Next, we are having of the valence bond theory is there, crystal field theory is there. These two are, you have to go through that one. Valence bond theory, nobody will ask, but Sidgwick theories you are asking. Page number 36, it is important, is given by the Sidgwick theory, how the octahedral electrons are enter into the, how they are excited state, how in the ground state the electrons are present. You have to draw that particular. Next is the isomerism. Isomerism is also asking in your examination point of view, 10 marks question, sometimes it's your 20 marks question. So third chapter is very important in the first block. Third chapter consisting of the 10 marks questions are 3 or 4 are there, 20 marks question is 1 is there. Or sometimes they are clubbed with the Sidgwick theory and Werner's theory, or crystal field theory, valence bond theory. That are also 20 marks question. So third chapter is very important for the essay type questions. Only short type questions are it. Only double salt. What is the meaning of double salt? What is the meaning of the coordination number and the classification of the ligands? These are short bits. Remaining all are the essay type question. Main important 36 page number. We are having the crystal field theory is there and also isomerism of coordination compound. There's the linkage isomerism, ionization isomerism. Okay. Ligand isomerism, coordination isomerism, geometrical isomerism, which are present in this chapter. You go through this one. So already time up. You will leave this one. So I will completed this one. You go through this simple mechanism is there. So you have to write one equation. That's enough for the each isomerism. The coordination isomerism. Compulsory bits this one. Okay. You leave that one. Only one student will be present.
Thank you, sir.
Okay.